who's come all the way from the materials department to give us a fascinating talk today on the experimental side of quantum computation. He's been doing some interesting work in an expanding group. It sounds like he has an army of students to do some great things for him. As is true, as he confirmed that he has won awards for collecting. So he asked me to emphasise that we were really in for a fantastic talk. So,
well, great. Thank you for that excellent introduction. I hope your hopes haven't been raised too much. It is a real pleasure to come over and talk here about our recent work on quantum memory in silicon. This strange picture here is an artist's representation of what this research is all about, apparently. So what we have here is a braid, which represents memory, and it's made of silicon, as anyone who's seen silicon would recognize. And inside we have a single donor atom, which we've been using. It's a phosphorus donor in silicon, and that has some nucleus that has spin. We can use that to represent information, and also it has a bound electron, which also has spin in the use of information. And as you can see, that there's a superposition of the different nucleus states, and that demonstrates representing quantum information. So I'll be describing the work in a little bit more detail than this figure would indicate later on. So to start with, I really want to give a very thorough description of the kinds of experimental techniques that are at our disposal for manipulating qubits that are represented by the property of spin. And then, having established that, I'll go on to describe then this principle of quantum memory, how we can move information between different degrees of freedom to get coherence lifetimes that go out to seconds. Then I'll explain how this can be scaled up to the idea of a multimode memory, or what we could think of as a quantum stack, where even though we have an ensemble of unaddressable spins, we can use holographic techniques to put in a lot of information and get it out in arbitrary order. And finally, I'll describe how these ideas, which are very much to do with memory, can actually be extended with the help of the measurement-based quantum computing architectures, and how it's possible to conceive of a model for a cluster-state silicon-based quantum computer. So I'll give a very, very brief outline on quantum information processing. I know it's a subject that many people here could give a much more thorough introduction than an experimentalist like me. But really what I find a helpful idea with quantum computers is to think of them as a processor of quantum information, and less of the fact that it's an information processor that happens to be quantum. So it's really the quantum information which is the key ingredient. And what we mean by that is, if we think about information as being represented in real physical systems, then quantum mechanics gives us, at least at the moment, the most fundamental laws of physics with which those physical systems are going to behave, and therefore quantum information theory is the general theory of information processing in these real physical systems. And so classical information processing is therefore only a subset of this, what happens when the system is only allowed to use a limited portion of the resources available. Here we have two examples of classical information processing. So the fundamental unit of quantum information is the quantum bit, or qubit. And here we can look at a fundamental unit of information as one which is capable of existing in two distinguishable states. When one then takes this fundamental unit and applies quantum mechanics, we can see from Schrödinger's equation that if the system is allowed to exist in only two distinguishable states, it's also allowed to exist in a coherent superposition of these two states at the same time. So therefore, the most general representation of quantum information, the qubit, can exist as some arbitrary coherent superposition of 0 and 1. And we can represent this conveniently on the surface of a sphere, the so-called block sphere. So the poles, we have the eigenstates 0 and 1, but our general qubit is allowed to exist anywhere on the surface of this sphere. So with this picture, we can then easily recognize manipulations of the single qubit. We can think about that purely as rotations of the Bloch sphere. And also, very important for the subject of this talk is the corruption of quantum information. What happens when the state of the qubit gets destroyed or damaged? And from the point of view of experiment, it's very useful to distinguish between two different kinds of corruption. So, with the qubit state represented as a point on the sphere, we can define these two angles, theta and phi, to pin down the state of the qubit. And T1 is a characteristic timescale for the corruption of theta. So this is in general an energy-changing process because it's changing the relative quantities of the 0 and 1 eigenstate. So generally, that is the slower timescale. And T2 is a randomization of the phase, really the pure dephasing, decoherence, where because there's no energy change, it's often a much faster process. So often we're trying to find to extend this so-called T2 timescale. So what are the kinds of physical systems that one can choose to build a qubit? If you start off on the internet with a web search, you can go to qubits.com and find that this gentleman, who has the record for the largest number of coupled qubits, is actually made this nice toy. And you read the qubit stands for quantum bits, which is all reasonable, which are a unit of measurement in the realm of science. I think he's getting a little bit confused with the Roman qubit there, but that is not so helpful in terms of a physical system. We look instead at other kinds of systems: electron spins, nuclear spins, ion traps, and there's even some theoretical papers on the quantum information processing capability of black holes. But I'm going to focus in this talk on spin qubits. So in spin qubits, I'm going to give you some examples of physical systems which are being actively studied, and then try to describe some of the experimental tools that we use, how to initialize them into some known state, how they can be manipulated, how we can measure their state, and finally how they can be coupled together to perform some kind of multiple qubit operation. So here's some nice pictures of real experimental systems that people are looking at. There's various kinds of quantum dot systems which exhibit the property of spin. So these can either be islands that are grown on the surface of a material that are small enough to have this quantum dot atomic character, or they can be defined by electrical gates that are placed on top of the material, again, to create the desired level structure. Other kinds of systems are, in a sense, more natural quantum dots. They're molecular systems in which there's some kind of trapping of an electron spin. And this molecule here is a carbon-60 fullerene with a nitrogen atom that's trapped inside. And so you can think about it as nature's own smallest atomic trap. And here, the atomic nitrogen has unpaired electrons, and it therefore has this property of spin. There are also various kinds of defects in a bulk. For example, we have nitrogen vaping centers in diamonds, which have very nice optical properties. And another kind of defect, which I'll talk about later, which is the phosphorus, atomic phosphorus impurity in silicon. And actually, as you may know, this is really the cornerstone. Putting dopants into silicon is the fundamental element of classical computation. And finally, just to throw in a little bit more of a wacky scheme, there's also electrons on helium. People looking at creating thin layers of superfluid helium, and individual electrons will float above the surface, bound by their image charge, and then they can be moved around the surface, and in principle have very good coherent properties. So then what I'll be talking about relates generally to this sphere of different kinds of physical spin qubit. So the spin is nothing more than the magnetic moment exhibited by certain atomic nuclei and by unpaired electron spins. And when we apply a magnetic field, we're given the two eigenstates which we call spin up and spin down, and these are then split by a quantity which is determined by the strength of the applied magnetic field. And we can use these two eigenstates, spin up and down, to represent 0 and 1. So first of all, to initialize them into some known state, we can simply make the field high enough and the temperature low enough such that the thermal energy is less than this splitting and all spins are cooled into the ground state. That would be one kind of brute force technique. And although for electron spins which have a much larger magnetic moment, this is possible to do in a realistic field. Nuclear spins have a much weaker moment, and so it's not possible in really experimentally accessible conditions to just thermally cool them in this way. Other kinds of cooling include optical pumping, where we exploit some kind of different selection rules in a level system where, for example, we excite both levels up with some optical excitation, but the selective relaxation back down to one of the particular eigenstates. So by pumping the system round in this way, we can eventually cool the system so that it's in a ground state. So having initialized the system, how can we then manipulate it into some other particular desired state? And here what we can do is really build on a long-established methodology of pulse magnetic resonance, so-called EPR in the case of electron spins, or NMR for nuclear spins. And this involves putting the system in a certain magnetic field and applying resonant radiation to excite the spins. Specifically, we want to go beyond the kind of spectroscopic applications that these techniques use to just understand the environment of a spin to solve the structure of a molecule. We want to really focus on pulse magnetic resonance that's going to apply very well-defined operations to manipulate the spin qubits. So in order to understand how pulses of resonant radiation are going to work, we need to first of all think about the evolution of the spin just in a static magnetic field. In a static field, the spin is going to process around the z-axis at some frequency determined by this energy splitting. So in order to simplify the evolution so that we don't constantly have to take into account this precession, we move into a rotating reference frame, which is rotating at this precession frequency omega naught. And in this rotating reference frame, the oscillating resonant microwave field that we apply suddenly turns into a fixed magnetic field in the plane. And therefore, by applying resonant pulses, we can create some particular rotation around an axis. It's also important to note that given this choice of rotating reference frame, if there's a small fluctuation in the magnetic field, then there's going to be a small change in the precession frequency of the spin. And it's precisely this kind of process which is going to cause decoherence. So any kinds of fluctuations in energy splitting are going to move the spin out of a phase with the rotating reference frame and cause decoherence. So there's just a little movie that I have here to illustrate applying resonant pulse radiation. So here we have an applied static magnetic field. So here we have some spin that's aligned with the static field, and in the rotating reference frame, the applied pulsed field is going to appear as an in-plane, as a temporary in-plane magnetic field. So the spin simply precesses around that in-plane magnetic field, and by choosing the phase of the applied radiation, we can choose the phase of this direction, the xy plane of this temporary field, and then we can therefore drive the spin around coherent oscillations, so-called Rabi oscillations. So here is another illustration of this process. By applying resonant radiation, we drive these resonant complete Rabi oscillations between the two eigenstates, and therefore just by choosing when to stop anywhere on this curve, we can apply an arbitrary single qubit gate. If we move off resonance, away from the rotating frame, the Rabi oscillations are then much shallower, and it's not possible to completely move from one eigenstate to the other. Here's some experimental examples of Rabi oscillations that I performed in this encapsulated nitrogen system. And you can see immediately that the oscillations die out very quickly. There's even a little bit of beating. And this is not decoherence. We've measured decoherence by other means in the system and measured it out to many hundreds of microseconds, and we can see, looking at this time scale, that the oscillations became much faster. So what we have here is a clear illustration of the limitations of gate fidelity. We can manipulate the spins, but crucially we need to be able to manipulate them with a high enough fidelity. So we then embarked on a study of the various kinds of error present with qubit manipulation in an effort to create these high fidelity gates. I found that in general there's 3 different kinds of things that can go wrong. So we can have an error in the rotation angle, we can undershoot or overshoot. There can be an error in the rotation axis, which arises from a changing phase of the applied microwaves, and we can be off resonance, as we saw here. What we found in our experiments was that the principal source of error was rotation angle, and furthermore it was a systematic error in the rotation angle. So for example, the pulse field that we're applying was just a little bit too strong, 10% too strong, so that every operation that we apply is over-rotated or under-rotated by the same amount. And this particular kind of error, a systematic error in angle, can actually be tackled using a composite pulse sequence. So there's this nice quote from Gandhi: an error does not become truth by reason of multiplied propagation. In fact, this is exactly what we do. We apply one shoddy pulse, and we follow it up with 3 further pulses that have exactly the same systematic error, and that somehow unwinds the original error of the first pulse. It's important to note that we're correcting the operator, not the final state. So we're creating a rotation operator that has this high fidelity regardless of the desired initial and final state. So this just illustrates how, given some fixed systematic error, a simple rotation has a fidelity that falls off fairly quickly, whereas this composite rotation is much flatter, so it's much more insensitive to a fixed error. And I'll show one more movie to illustrate how this could be. So let's say here we have this initial state that we're pointing along somewhere in the plane, shown in red, and blue just shows the reminds us which way the magnetic field is pointing. So let's say I want to apply pi rotation, and so some of the spins maybe have been rotated by the correct amount, some haven't quite gone far enough, and some have overshot the mark. If we then apply the 3 further pulses with the same systematic error, but around the specific phases that we've chosen, then you can see that everything collapses back, and so that they all end up where they should have done. And so it's this kind of technique that can be used to correct systematic errors in the experiment. And here's an example. We're just zooming into an early part of the Rabi oscillations for the system, and you can see that the Rabi oscillations, which are shown in the light grey, they're decaying away. If you apply this composite pulse technique shown in the dotted lines, we can see that the gate is much more robust and there's no visible decay. So I'll just outline now a few ways in which we measure the states of electron spins, starting with the most common, which is cavity detection. It's also the least sensitive. So here we have some pulsed microwave source that we're using to create these short coherent pulses of high power resonant radiation. These are sent down into some sample which is sitting in a high Q microwave cavity, and then these spins process in the cavity, emitting a very weak microwave signal that's then fed into a detector. And this kind of measurement has a sensitivity down in the limit to about 10 to the 10 spins. Very far from single spin sensitivity. So really we need to start looking at more innovative ways to detect the states of individual spins. And here's the first example of where we are making use of multiple quantum degrees of freedom. We're looking at an isolated spin, just saying this does not have all of the ingredients that we need for the most powerful qubit. So let's interact this degree of freedom with something else, like charge or light, in order to make a more precise measurement. And so the next kind of measurement we can do is electrically detected magnetic resonance. So it's the same initial part, same pulse source, a sample in a cavity, but upon the sample, we actually, the sample is going to have some resistance, and we're going to measure the conductivity of the sample. And due to certain spin-dependent scattering processes in the material, we can relate very small changes in the conductivity to changes in the spin state. So again, this is something that you need a particular kind of material to implement this. But we can see, and this is looking at the conductivity of the material as we apply microwave pulses, and we can see Rabi oscillations, coherent oscillations, in the conductivity, exactly as we did before with cavity detection. This kind of measurement has a sensitivity that can potentially go down to the single spin level. I'd say most experiments now are in this kind of region between 1 and 1,000 spins, but there's some promising demonstrations of single spin sensitivity. Finally, one of the most sensitive methods shown so far is not electrically detected, but optically detected magnetic resonance. So again, here you need some kind of coupling to another degree of freedom. There's a spin represented here in the ground state, but we can take some optically excited state and use appropriate selection rules to then observe changes in the optical properties of the material depending on the spin state. So here, for example, we have a spin up and spin down. We optically excite, but in this particular level structure, only one of these excited states is going to decay into a dark shelving state. And so we can cycle this system round and round, observe photoluminescence if we're in the 0 state, but if we're in the 1, we'll very quickly go into the shelving state and see nothing at all. And here's a little illustration of this in action using trapped ions. So they're going to start off in the 0 state, they're constantly being illuminated, and so they're giving off photoluminescence. So here they are glowing. Now they're all flipped into the 1 state, where they pop into the shelving state, and the shelving state is metastable, so on the time scale of seconds, they decay back down into the 0 state. So each one of these little white blobs is an individual ion whose spin we're measuring using this kind of optically detected means. And so this kind of sensitivity, as you can see for yourself, is certainly down in the 1 spin ratio. So finally, what about coupling different spin qubits together? I'm going to take the example of 2 very different kinds of spin, an electron spin and a nucleus spin. And as I said, these have very different energy scales, only the electron spin splitting is much, much larger. So in general, for these 2 coupled spins, we have a 4-level system. We have the interaction of the electron spin with the magnetic field, the nucleus spin with the magnetic field, and so we can excite and manipulate the electron spin using these microwave transitions, and the nucleus spin using these lower energy radiofrequency transitions. But at the moment, without any coupling between them, it's not possible to distinguish, it's not possible to apply any kind of controlled operations, because the frequency, the resonant frequency of an electron is the same regardless of the state of the nucleus. But if we allow ourselves one more term, a Hamiltonian, some kind of interaction between the electron and the nucleus spin, so a hyperfine interaction, then this kind of level diagram splits, and we can now distinguish between the energy of the transition of the electron spin depending on the state of the nucleus. So for example, if I wanted to do a controlled knot operation, if I wanted to flip the electron dependent on the state of the nucleus, then I could apply a high pulse resonant only with this frequency, and then this would rotate the electron between the down-down and the up-down state only if the nucleus was down. So we can use this kind of spectral selectivity to perform a controlled operation. And that would be an example of how that would be representing 2 qubits. So that was just a summary of the various kinds of tools at our disposal when manipulating spins. Now I'd like to specifically compare 2 kinds of spin, electron and nucleus spin, look at their advantages and disadvantages. So as I've already mentioned, electron spins, they've got a larger moment, so they have a greater polarization, and so it's easier to initialize them into some pure starting state. They also benefit, because of this larger moment, from faster gate operations, both the time it takes to manipulate a single qubit and also the strength with which they interact with each other. The final advantage is that, following the techniques outlined earlier, in general it's easier to detect single electron spins than nucleus spins. Conversely, nucleus spins have much, much longer lifetimes. Both this T1 time and this T2 time are generally orders of magnitude longer in nuclear spins. And that is the main advantage that nuclear spins have. So from contrasting these properties, it seems an obvious route to take to try to use electron spins where possible for any kind of processing application, and then move states into the nuclear spin for memory. Now it's important to note at this stage that when we're dealing with quantum information, and therefore with the desired quantum memory, that there's a no-cloning theory in quantum information that forbids us from copying state. So if I wanted to think how a classical computer implements a memory, I have a bit of information I want to store, I would copy it onto the memory, maybe check that they're the same for error correction, and then delete my original copy. I can't do that, perform that kind of process with quantum information. It needs to be a coherent transfer from one degree of freedom into another, or in other words, a swap operation. So how would we do this with the coupled electron spins? So here's the level diagram I had up here before. For those that are familiar with quantum circuits, the swap gate can be implemented with 3 controlled knots. And what I want to do is perform this swap between the state of the nucleus and the state of the electron. In fact, I can slightly simplify this swap gate by applying only 2 controlled knots if I predefine the state of one of the qubits in a known state. But going back to the implementation, so let's just say that I have some qubit that's represented between these 2 states. So it's an electron, a coherent electron state. We've defined the nucleus to be down, and so this qubit represented between these across this electron spin transition is going to decay the very fast decoherence times of the electron spin. So we apply a resonant RF pulse across this transition, so flipping these 2, and we create some kind of entangled double quantum coherence between these 2 levels, and then finally a rotation around this transition moves the state into one which is stored entirely across this transition. This is a nuclear spin transition, so this state is now going to decay with the much longer properties of the nuclear spin. And then to read it back, we simply reverse the process and return the state into the electron spin. So really, these 2 controlled knot operations are the cornerstone of the memory process. The particular physical system that we first attempted to perform this in is phosphorus donors in silicon. A particular variety of silicon, the silicon-28 isotope, is the most naturally abundant, but there's still 5% of other isotopes that have nuclear spin. And these can lead to decoherence and broadening. So we had to get single crystals of isotopically pure silicon-28. These are produced from various trading sources in Russia that have experience in separating things of slightly different mass. And it's also important to use single crystal samples to reduce strain, make sure that all of the spins are in a very homogeneous environment. And finally, although we're looking at an ensemble of spins in this material, we really want to be studying the physics of an isolated atom. And we can only do this if the concentration of impurities is low enough that they don't interact with each other. So we work with a donor concentration down below 10 to the 15 per centimeter cubed, so we can really view each donor in isolation. It's also a nice system because it relates to a very influential proposal for how one might build a quantum computer that came from Kane back in the late 90s. So our experiment was to, first of all, take the electron spin associated with the donor and put it into some particular coherent state with a microwave pulse of some phase. And then we apply a whole sequence of pulses to move this state into the nuclear spin, refocus any areas in the nuclear spin, and then transfer it back to the electron. And some long time later, 50 milliseconds later, we observe a piece of coherent electron, a coherence across the electron spins in the ensemble, so-called spin echo. So that was a promising start, but the key is then that we varied the phase of this initial microwave pulse, varying the coherence of the electron spin state we generate right at the beginning of the sequence, and we see that this coherence that appears right at the end, 50 milliseconds later, follows the phase of the original microwave pulse precisely. So this really illustrates the implementation of a memory of storing an electron spin state here for several tens of milliseconds. And this was covered in the New York Times, that described this as the world's smallest storage device in the nucleus of an atom. Someday you might be able to take business data off a disk drive and move it into the nucleus of an atom. Well, typical journalist slant on it. I noticed that you can click on disk drive and buy a disk drive. I think that's the way they make the money. You can't yet buy the nucleus of an atom. Hopefully after this research becomes sufficiently developed, that will also be a high business. So, so far what I've shown you is we created some electron spin state and just managed to recover it several tens of milliseconds later. To really show that we've done what we've said we've done and really store this in the nucleus, we need to take a look right in the middle of this process and measure the nuclear coherence directly. And so this measurement is essentially a measurement of the nuclear magnetization during the middle of the memory process. You can see that the nucleus itself also has a phase which is also varying with the phase of the original electron coherence that we generated. So indeed, we're storing this state in the nucleus and then getting it back out. To be completely general, we need to look at a set of all possible orthogonal initial states, so these X, Y, Z and identity states that can make up a general initial state. And we need to perform a tomography of the density matrix to show that each of these initial states is equally well stored. So we might look at the plus X state in the initial one that we generate and the one that's recovered, and by comparing the fidelities of these two density matrices, we get a storage fidelity there and back combined 90%. And then we can do this for each of the different possible orthogonal basis states, and in each case get some kind of fidelity around 90%. Now this infidelity is limited precisely by the kind of error that I was talking about at the beginning, this rotation angle error. And in fact, we found that by applying this composite pulse sequence that I introduced earlier, we can improve this fidelity to 97%, and I believe we can go further. So the fidelity of the memory, I think, is very high. The next key question is the limits of the storage time, because after all, this was why we've gone to this trouble in the first place, because we've been promised that the nucleus spin can hold quantum information robustly for much longer. So really, all we want to do is an NMR experiment on the nucleus spins in the silicon and measure what their T2 is. However, we're operating in a regime which is far, far below the limits of sensitivity in an NMR spectrometer. So we really need to use this memory technique and just see how long, how the recovered magnitude of the electron spin state we've stored, how that varies with the storage time. So that experiment is exactly what I described earlier, and we just vary the storage time and we do the sequence to extract the memory out. It turns out that there is a fundamental limit of the memory time, which is given by the properties of the electron itself. Because the electron and the nucleus are strongly interacting, the relationship between the T1 of the electron, so that's the time scale on which it flips, versus the nuclear T2, and that's the time scale on which it loses phase. And we can see that because a flick of the electron spin is going to dramatically change the magnetic field environment of the nucleus, cause it to lose phase. And so we see that the nuclear T2 is always going to be bounded by twice the electron T1. But I said that T1s are often much longer, and in fact, the electron T1 goes out to seconds, even hours at longer temperatures. So it looks very promising that we'd be able to get a coherent memory that goes out for many seconds. And we see that it follows this trend very closely down to about 7.5 Kelvin. And at lower temperatures, some additional mechanisms start to come into play. And that will tell us really about some tiny concentrations of impurities in the material, and allows us to go back to the crystal growers and provide them with information to help them make better samples. However, the best time that we've been able to measure so far is a decoherence time of 2.5 seconds. So this is measuring the electron spin coherence that we've recovered in this point here, 1 second after we generated it, we're already getting a appreciable amount of the original coherence back. And I don't believe that this time scale is in any way intrinsic, and that with a bit more effort we should be able to go up to tens of seconds. I think really the interesting thing is looking at what are the mechanisms behind coherence and what this can tell us about materials. So there's various different factors that we've begun to investigate. One of them already mentioned is temperature. That we have this nuclear T2 which is bounded by twice the electron T1 for some range, and then reaches some kind of intrinsic limit. And then we've looked at how that intrinsic limit varies on various materials parameters, looked at effects of impurities and silicon-29 concentration. I won't go into the details, but it's providing us with some interesting tools for studying the materials. Also, although we've demonstrated all of this with phosphorus-doped silicon, the idea applies to any system where you have a coupled electron and nucleus. And so we've gone on to look at how this quantum memory might be applied using nitrogen atoms in fullerenes and other kinds of defects such as nitrogen diamonds. And so here's some work performed by one of my students, Richard Brown, who's looked at exactly the same idea, taking some original electron coherence, storing it in the nucleus and recovering it again, and he got a nuclear memory time of about 50 milliseconds. That's about 2 to 3 orders of magnitude longer than was previously possible in that system. And in diamond is a very nice system because you can operate it at room temperature. And here we found that the nuclear memory time was 4 milliseconds at room temperature. It's bounded by this hard limit of twice the electron T1. So the electron T1 is about 2 milliseconds. So that could also be a very nice system if one could find a good way to couple different spins together. So finally, I'll just show you a summary slide of various kinds of T1 and T2 in the solid state, ranging from superconducting qubits, molecular magnets, quantum dots, and so on. And in each case, how using a quantum memory has allowed us to extend these times. So this is an NC60, an extension to longer T2. And the diamond, and finally, in the case of phosphorus, really moving to a new regime of T1 and T2 times. Another way to look at this is in terms of T2 and the operating temperature. That in each of these cases, using the memory has allowed us to move into a regime which has higher temperature and longer coherence times. So far, I've just been talking about the storage essentially of 1 qubit across the ensemble. And each of the electron spins is stored in state coherently into the nucleus spin. But really, this is not the best use of resources. And because we have a large number of spins in the ensemble, we have the potential to put in many bits of information. And we can do this, for example, using collective modes and applying field gradients that would create a spatial phase variation across the ensemble. Therefore, use this like a kind of holographic memory. This is quite an old idea. We found in the 1950s, Hahn and co-workers were being funded by IBM to look at creating a serial storage memory using an ensemble of nuclear spins. They found it wasn't so bad compared with the mercury delay line or magnetic tape that they were using at the time, though, of course, rapidly such an approach became fairly uncompetitive. So for classical information processing, this is not really the way forward. But for storing a quantum state, it's quite a powerful idea. And we can do is consider how we can store the state of a single excitation, like microwave excitation, in other words, a single microwave photon within the ensemble, and then apply a certain phase shift, a phase gradient to the ensemble to write that excitation, to label it in a particular way so that it can then be recorded separately. And this is possible with electron spins. It's possible to generate circuits that operate with single microwave photons. So we're going to begin to explore this idea using very, very weak microwave pulses, moving towards the limit of single microwave photons. So this idea of holographic storage, just to recap it, let's say I write my first qubit into the system, and this qubit goes into the k equals 0 mode of the ensemble. There's been no gradient applied. I then apply some kind of field gradient, and so this excitation has now been written and has some phase profile that we just call kg. Then I can put in a new excitation, and that already has a new phase, because every new excitation is written into the k equals 0 mode, second field gradient, third qubit, and so on. The limit of the capacity of this kind of memory is roughly the square root of n for an ensemble of n spins. So we can begin to explore these ideas applying magnetic field gradients. I'll explain more in this slide here. So for example, we can apply a constant magnetic field gradient and a sequence of very weak excitations. So weak that they excite on average such a small fraction of the spins that subsequent excitations all have roughly the same intensity. We haven't really consumed the magnetization of the ensemble. So at this time 0, we can consider this excitation as having been written with 7 kg, 6 kg, and so on, because through time they've constantly been acquiring a special phase gradient from the magnetic field applied. And then by either reversing the gradient or an equivalent thing, which is just to flip all of the spins and allow them to process to field and the reverse field gradient, we get a set of 8 spin echoes, each of which relates to the original excitation we put in. It's very important that these excitations are weak. We can look at what happens when they cease to be weak excitations. You can see all kinds of various interference effects. But what we really want to do is explore the limits. And here we put in 100 weak microwave pulses, and here we randomize the phase, and we randomly chose between 0 and 1 to write, apply this refocusing pulse, and we get in reverse order each of these excitations. So this is behaving as a quantum stack. And we can use the nuclear spin in exactly the same way as we did before to allow this quantum stack to benefit from the very long second lifetimes of the nuclear spin. So here we apply 8 very weak microwave pulses, write them into the nuclear spin, and sometime later bring them back to the electron spin, and we get each of those 8 microwave excitations. So we can imagine now a general memory for storing any microwave photon using transfer to the nuclear spin that is capable of storing states out to seconds. And just in the close of the talk, I'd like to describe how we can move beyond memory with this idea to explore how it's possible to scale this towards something that actually performs computation. So there's a few aspects of the work I've described that show a limit in the performance of the memory, performance of the nuclear spin, due to the coupled electron spin. So we have this bound of twice the electron T1 that limits the nuclear T2. We also have this limit here, which perhaps might also arise from coupled electron spins. So it's obvious to ask, what happens then if we, after we've written the state of the electron into the nucleus, surely we can just get rid of it. The information is now stored in the nuclear spin. So let's investigate that. Let's remove the electron spin and see now whether the information can last for longer. Another important question is, which is strongly related, is how does the actual process of removing the electron spin? It's quite a disruptive process. How will that affect a coherent nuclear spin state? And then finally, let's have a look at computation. Skip these. Go straight here. So, and this idea builds heavily on the work of measurement-based quantum computing, the idea of a cluster state as a powerful resource for quantum computation. The nice thing that this does, at least experimentally and elegantly from the point of view of theory, is to separate two processes. One, the process of generating a resource which can perform computation. And second, the act of consuming it in order to actually drive a computation. And And so it allows us to focus on these two elements separately. An example of a useful resource is a cluster state, a network of entangled qubits. And what we require is to be given such a network, and we require the ability to measure out each of these qubits in some arbitrary basis. The performance of this as a measurement-based quantum computer is then entirely given by the speed with which we can perform these measurements, the fidelities of the measurements, and yet this model is capable of performing universal quantum computation. And so we can kind of think about this as a dimension computation, time and line computation depth. So how can we do this in silicon? Well, in this model, we only require global microwave and RF pulses. So anything that we do to manipulate the states of the spins, we're going to be doing to all of the spins in the ensemble. The only thing we're going to require is local measurement. But we can imagine the local measurement taking the form of the electrically detected measurements that I described in the beginning. Because electrically detected devices can be made on the scale of tens of nanometers. So we can just abstract this to a set of pixels, where each pixel is then representing a phosphorus donor, so it has some phosphorus nucleus spin and electron spin, and some measurement device. And these don't need to be particularly far apart, they can be hundreds of nanometers apart. In fact, it's good if they're hundreds of nanometers apart, because we don't want any actual through-space interaction between the spins. So what we first of all do is polarize the nucleus spins, initialize everything, and then put both the nuclear and the electron spins into the plus state using global pion 2 pulses to both kinds of spin. We can then apply a controlled phase gain between the two spins, and that moves them into an entangled state. This kind of selective rotation is one that we perform routinely in the lab. The next key step is to move all the electron spins along one pixel. So donors in silicon can be ionized using electrical gates. So it's possible to consider moving the electron spin from one donor onto the next while maintaining coherence. In doing so, separate the two spins that have been entangled. The electron is now sitting on a new nuclear spin, and again, through a global operation, we can entangle that with its local nuclear spin. We can then move all electron spins down one pixel, perform the same entangling operation, but now in a small number of steps, we've created potentially a very large cluster state, because we can do all of this in parallel. And finally, we just measure out the electron spin and leave the nuclear spins in a cluster state. Maybe, okay, well, yeah, that's the controlled phase operation. So that's the movement of the electron spins. That's the nuclear spin cluster state. The kind of measurement that's been performed, as I said, electrically detected measurement is down towards the single spin level. Recently there were some papers that appeared on the archive today that showed, in recent times, that showed the measurement of the single donor spin. So that element of it seems quite well developed. The area that needs the most experimental attention is moving electron spins whilst maintaining coherence. But with that, a lot of the other key ingredients are already demonstrated. So, in summary, I'd just like to recap the key points. That electron spins is an ideal component within what we call hybrid quantum systems that have multiple quantum degrees of freedom. The nuclear spin of phosphorus in silicon has memory times that exceed seconds, and therefore can be a very powerful memory element. This can be scaled up to store a larger number of qubits in a multimode memory. And finally, this kind of interaction in these between electron and nuclear spins could be harnessed towards a measurement-based quantum computer in silicon. So let me just end by acknowledging all of the many people associated with this work, both here in Oxford, in Princeton, and